calculus. I've got 3 students today that I know are out for various reasons that already contacted me, so I'm trying to video the lecture today. And I'm not sure my batteries will run the whole 75-minute period. So at some point I may have to swap batteries just to get the rest of the lecture for them. But I'm Dr. Hopkins, and we should have 35 in the class. I currently count 29, so I think we're still missing 3 that may wander in a little bit here with that. So, and this is business calculus. And today we're going to try to get through most of section 1. We probably won't make it all the way through section 1 with that. But we're going to be using clickers for roll and daily participation points. And so not only are we using clickers at 8 o'clock Tuesday, Thursday, I believe they're being used in Wheeling 101. And so unless one of us does something special, all of our clicker answers get collected by both units whenever they're collecting answers. And so we're going to use what will be known as frequency BB. We're going to change from the default frequency. So in your clicker unit, if you hold the power button for about 5 seconds, the power button or the power light will start to flash. When it flashes, enter B. Wait just a little bit and enter B again. The first B, the vote status will be red. The second B, the vote status should go green. We've now just switched to the BB frequency. If your clicker ever turns off during class, when you turn it back on, you'll need to switch back to the BB frequency. And then whenever I'm collecting responses, make sure your clicker's on the BB frequency and submit answers. So signing on, you're going to see names start to appear. I think they come in alphabetical order by the last name with 3 letters. So if your 3 letters are, say, A, B, E, enter it A, wait a little bit, just maybe a second, A, B, E, as opposed to A, B, E as quick as you can push them. It doesn't quite respond that quickly to multiple keystrokes. So A, wait a second, B, wait a second, E, wait a second. When you get the 3rd letter entered, you should see your name change shade and have a number associated with it. That's actually the number on your clicker. You don't have to worry about that. But that clicker is now assigned to you for the class period. Every time you use the clicker, another response will be recorded to your name. And after class, I go and look to see, did everybody respond to most questions? Just to make sure everybody's participating with that. So we will take roll with this. And it's possible somebody's name's not on here, because I think I was supposed to have 35 and this roll says 34. So I thought I'd been checking it recently. And the last 10 or so aren't on there. So let me actually move ahead, and we should now have everybody. So typically as you come in, this will be on the screen showing you can find your name, sign in, and you'll be ready for the day's class. And it is possible, for reasons I haven't figured out, that you may sign in, your name changes, and then some later time it shows back up. So definitely kind of keep watching to make sure you don't accidentally show back up. I don't know what's up with that. But let's see. So is Trenton Holmquist here? Okay. Okay, you are now signed in. What about, is it Maximilian? Is Maximilian here? Or? Oh, okay. Oh, and you're not signed in. All right. So the 3 that aren't signed in are the 3 that had contacted me that they would not be here. So, although I'm not sure why it says 29 are registered when it should be 31. Sam and Michael, I think, probably already logged in, but I'm not quite sure why it lost you. if ever there's a day you come late, still pick up the clicker as you come in. Enter the responses at the end of the class. I'll pull this back up and you can sign in at that point as well. So it keeps track with the number, and then in another place it tracks the number with the person. So it'll keep track of what every clicker unit responds, but until you pair that clicker unit with your name, I won't know who is using any particular clicker unit. I'll know the answers that clicker unit gave with that. So, oh, now I took off Paul. I don't know what's... So, actually, is Paul here? I was looking... Was there anybody whose name was not on here? Because I'm kind of thinking I may have missed somebody. I'll double check on that. Okay, well today we're going to go over the syllabus and then we're going to get started with some material in class. And a bit of an overview of the course, but it would actually help to dive in some introductory material as well. So, are there prayer requests as we get started? Before we go over the syllabus? I know it's the start of the semester, but one of the students not here is because of illness, and I was putting up signs for a colleague who's out ill today, and so I know lots of illness, and so you're how do I make sure not to get it? So follow good hygiene, I think is the only suggestion I know on that, but okay. Shall we pray? Lord, I just thank you for the opportunity for new beginnings and to be able to look and see how people have attempted to describe your world with calculus, that we can begin to understand some of what goes on, and understand better how we measure how things change, how we measure how things accumulate. And I just pray that you help us in that, help me in explaining the concepts, help the students in working, help them to stay healthy, and if they get sick, help those sicknesses to be brief so that they can continue in their studies, and just guide and direct us this semester. This I pray in Jesus' name. Amen. So the syllabus is posted in Blackboard. So from the portal, you can go to Blackboard, and it should show all your classes that the instructors have opened up. It is possible some of your classes, the instructors may not have gotten the course open yet. Don't panic on that until after you go to class. But mine is open, and in fact, I have due dates in there. So if you look in the calendar feature, you should see due dates for the class. Pretty much every day that we have class, there are participation points. So you'll see what looks to be an assignment of the date. That's the daily participation points. 6 points if you were here and answer most of the questions, and most of them correctly. What detracts from participation points is if you're here, but then there's a whole string of you didn't answer anything. And it records that information, so I would know, there's a whole string you didn't answer anything. So that's one thing about the clickers. Another thing you'll see, pretty much every day there'll be a homework assignment. We'll cover some lab material. There'll be a homework assignment. That'll be on Blackboard. I won't always get to it because it's usually at the very end of the lecture, and if I run just a little short of time, I don't get to that, but it's on Blackboard. You can see the assignment for that day. That is due at 4 p.m. of the next class period, which allows you to work on the homework, come the next class period, ask some questions, get it finished up, and then turn it in. You can bring it by my office sometime later in the day to drop it off. A lot of times students have it done, they can turn it in class with that. So, but we also have the lessons. I do try to get my PowerPoints out there in advance. Occasionally I make some last minute changes, so there may be a couple things different in the PowerPoint I use, but if you'd like to print out the PowerPoint in advance, those typically come up at midnight 2 days before. So this particular PowerPoint was available at midnight on the 23rd, so all of yesterday you could have printed it out. I think I have it in handout form so that you've got 3 slides and some spots for notes next to the 3 slides. you want to take notes on that, you can do that. The assignment shows up during class, and I try to be specific what day it's assigned, when it's due, and the problems. So this will show up at 8:30. One thing about our textbook is it's freely available online, and I'll point that out a little bit, but I think having a print book is also very useful, but it does not have the answers in the back. So I'm trying something different this semester. I do have answers, but when you turn in the homework then, I will need to see more than the answers, because they're available. Part of mathematics is communicating about your result, showing how you got that result, and just the answer doesn't do that. So it would be good practice on communication to show your work. Typically on the exam, the directions will be show all necessary work. Don't stress out over what's necessary. Show enough that you could follow it, that somebody else could follow it, and definitely so that I can follow your work. So if there's a mistake, I can find out exactly where that mistake was and deduct accordingly, or point out where the mistake is. Because, I mean, we all can make mistakes in math. We want to learn from those. And if all I see is the final answer, neither one of us can learn a lot from where the mistake was, because we don't know where it was, we just know the final answer is incorrect. So the answers will be there, and then the class period after I hand the work back. So this first homework set 1-1, you'll turn in next Tuesday. Thursday I'll hand it back. A key will come up Thursday then, kind of during class, that'll have more complete solutions. So there you can see more of the work of how you got the problem, how you could have approached the problem. So typical class period will start with questions on the previous homework, 15, 20 minutes or so, and then we'll move on to new material. So the syllabus is in here in terms of the lessons. Also, there are links to the textbook. So there's one link that takes us to the online textbook where you can go by section pretty much. We're going to cover section 1-1 today. And it looks pretty much exactly like the print textbook. But there's another version of the textbook that looks a little different, but it has all the information. Well, it has nearly all the information in the print textbook, but it has one additional feature that the print textbook does not, and the other online version, it has, for some of the examples, a video. So if you look through and you see an example, sometimes just seeing it in print isn't enough. It'd be nice to see somebody work it out. This version of the book does have it worked out, some of them, so they have some videos embedded. Unfortunately then, this version of the book doesn't have any of the exercises at the end of the section. I don't know why they put in videos but then took out the exercises. I would think if you were going to sort of duplicate much of the book and add to it, you would leave the exercises in there, but I have not found the exercises in here at all. But they do have all the sections. But the example videos I think could be helpful as well. So the syllabus is here, as are what I call some worksheets that I'll pull up at times during class to show some illustrations, do some extra practice problems from some of these worksheets. So in terms of the syllabus, we do meet 8 to 9:15 Tuesday, Thursday. Typically we will take all 75 minutes. I don't think we get out early terribly often. I have office hours after this class, and also Tuesday, Thursday afternoon, Monday, Wednesday, Friday, 9 to 9:50, and then Monday afternoons, 2 to 2:50. I'm also available other times for appointment. There's a link to the textbook here as well, as to where you could get it online, but I think having a print book that you can look at. There are a few errors in the print book that I've discovered, and I've tried to put those all in one location here in terms of some errors. So early on, page 7 and 8, there are a couple errors in that. So even people putting together textbooks can make mistakes. So just because you're looking at something, if you're thinking, I'm not sure this makes sense, ask about it. It could be a mistake in the text. Typically, a little bit of explanation. Oh, I understand now. So don't just think I can't ask any questions. Be free to ask questions of me, or even by email. There's a comment on page 7 I'm not understanding. I can look at it and let you know. In fact, if you find an error in the book that I've not already found and indicated here, I'll give a few bonus points, some extra credit points to put into your grade for finding those errors and reporting them. So, we're going to be looking at calculus, and when we do look at some applications of a calculus, I'll try to pull out applications related to business fields. The business setting is certainly where I have a weakness with that, but I've got a few ideas on some things I can bring in to maybe help with that this semester. But we're definitely going to be looking at the ideas of calculus and hopefully seeing, well, how those could apply to business settings. If you don't get your homework in on time, I would still say get your homework in. It will lose 10% each class day late, but that is better than going in as a 0. Each homework set is 10 points. And there'll be 17 or 18 of those, and I will drop, I'm going to be about 15, I'll drop 2 of the low ones. But it's much better to even get a 7 or 8 because the homework was late than 0 in the homework. Participation points, 6 points every day, except for the days we have tests, but 6 points every day. If you are absent, if I don't hear from you as to why you're absent, I assume it's an unjustified absence, and it'll go in as a 0. If you are absent, with a justified absence, it'll initially go in as a 0, but the next time you come, I will average that time with the time before the absence to replace the 0. I try to do that right after class, so if in a day or two after your return to class, you're still seeing a 0 there that you think that was a justified absence, remind me of that, and I'll go back and kind of check. It is far easier to think back in the last week or two than at the end of the semester, oh, that absence back on January 30th, I think I was sick that day. It's much better, right when you come back, to tell me, oh, I was sick that day, let's get it fixed then, than after the fact to come back and try to figure out, were you here or not. Also in terms of exams, if you happen to miss an exam because you're sick, some sort of family emergency, university business you would know in advance, let me know as soon as possible so we can arrange the makeup. I like to give tests back the next class period, but I also don't want to give them back before everybody's had the opportunity to make it up in case somebody missed. So the sooner we can arrange to get it made up, the better on that. But unless you provide me some justification, it goes in the grade book as an unjustified absence. If there's inclement weather, you use good judgment on whether you can get here safely. The university typically does have class. They're very rare that classes are canceled for inclement weather. The assumption being most students are on campus, and you just will be going to class as opposed to deciding, oh, let's go somewhere else in inclement weather. No, let's come to class with that. But if you don't think you can get here safely, err on the side of safety. I'd much rather hear from you decide later in the day, oh, I could have gotten there safely, than to decide in your hospital bed, oh, I guess I couldn't get there safely. Err on the side of safety with that. So here's how the grades will be determined, 90, 80, 70, 60 scale. We do have a tutor room that will be opening next Monday, open Monday, Tuesday, Thursday evenings from 6 to 10 in Wheeler 126. Definitely I would encourage you to try to keep up. The material very much builds from one day to the next to the next. So if you miss a day, still try to look at the homework, look through the section to see what we covered, do what you can, come by my office hours, because the next lecture will make far more sense if you at least grappled with the material before the next time. If you have any kind of disability that would impact your learning, I need to know about that so we can discuss whatever kind of accommodations are appropriate in your situation. And here is our tentative order of topics. There's a chance this first exam might go back a day. There's a meeting in Jefferson City on March 1st. I believe that I'm invited to go to, that I'm trying to decide how it fits, and the best way it might fit would be if our test was that day. So I need to think about that some more. But the test will certainly be around these times. The final exam will definitely be, what is that, Wednesday, I believe, May 16th. That's the time set on the master schedule. And in general, any time set on the master schedule, that's when instructors are to give those finals. And you need to schedule around that master schedule. You know, don't get plane tickets to leave on Tuesday and try to do all your finals early. That's too complicated to do, and we want students to understand the expectation is you will come the day the final is scheduled. So, are there questions on the syllabus? As you look through that a little bit more later, if you've got questions, feel free to ask them. So let's see. I think I noted all that. So as we think about business calculus, I want to talk just a little bit about, well, what's the purpose of mathematics in the first place? And the history of solving math problems really goes way back in history. I think they found ancient Egyptian cuneiforms where there's some word problems that look pretty typical to word problems you think about now. And so that idea goes way back. And part of understanding problems is realizing we can look at them from different forms. This first worksheet I've got here, in fact, talks about the idea of function, which is what we'll start in a little bit. But even with functions, there are different forms we could look at them. We could look at them in terms of equations, tables, graphs, or information about the function. So there's different forms we can look at, and sometimes one form will prove easier to understand than another, or one form would give us more insight to the problem than another. So realizing there are different forms can help us in understanding them, can help us in explaining the solution to others, perhaps realize they didn't look at it in the form we did, and so maybe the reason they're not understanding it is they were thinking a different form. And these ideas apply not just to mathematics, but any other sort of problems. I mean, say you're having an issue with a roommate. You've got a form of what the problem is. As you start talking, you may realize they've got a different form of what the problem is, or maybe they had no idea at all there was a problem. But in discussing, you may come up with a totally different form of the problem, and that helps you solve the problem. So realizing you can come at a problem from various directions, and that can help you in understanding the problem. Mathematics sharpens the mind. It develops our deductive reasoning skills. And knowing some mathematics can increase your motivation, or knowing some of the way it can be used can increase the motivation. There are a list of statements called standard practices of mathematical education. Things that math educators at all levels should seek to develop in their students. Things like helping students make sense of problems and persevering in solving them. We will have some problems in business calculus that are fairly challenging. We cannot just say, oh, that's tough, I can't do it. I mean, we've got to look and figure out how can we persevere and solve. I mean, if you're in a business and there's a challenge of something, you can't just say, oh, that's a really tough problem. I hope somebody can solve it. It may be your job to work on it, persevere, see if you can come up with some sort of solution. And yes, that can be difficult, it can be intimidating, but perseverance is certainly a key factor in that. Reason abstractly and quantitatively, we'll do some of that. Construct viable arguments and critique the reasoning of others. This is a main reason I want you on your homework, be sure to show your work. That's part of constructing a viable argument. Math is not just about, here's the answer. It's about the process of how we got the answer. And if all I see is the answer, I don't know your process. You could have just copied the answer from the key I gave you. That doesn't show me you understand the process, doesn't show me you can explain the process. So very much wanting to understand the process. Model with mathematics. Certainly in business calculus, we're going to be working with some equations that are attempts to model things that happen in business. we'll do a lot of looking at like the cost function, where someone has come up with a model that we think the cost function looks like this, or the revenue function looks like this, or the profit function looks like this. And then can we analyze that? But certainly coming up with that model in the first place is an even bigger challenge than what do we do with it once we've got the model. So there are a couple times we'll look at cases where we in fact have to come up with a model ourselves and then try to analyze it. Use appropriate tools strategically. We will use the graphing calculator. The worksheets I put together, a lot of them have what are called dynamic features. I can change things and we can immediately see the results. That hopefully will show us, well, what's really going on here. How is changing this affecting something else? Calculus is very much about a study of change. How are things changing? How rapidly are things changing? What exactly is changing? So we're looking a lot at change in calculus. We will need to attend to precision. We want accurate results. Look for and make use of structure, and look for and express regularity and repeated reasoning. So as I said, the reasoning and viable arguments will be expected on homework. More than just the answers are needed on the homework. And as you think about that, think of how somebody else would need to follow your work, or even yourself. You come back tomorrow, the answer by itself isn't going to tell you how you got that. You've got to write down at least enough for you to follow your train of thought, because if there's an error in there, we want to identify where that mistake is so we can fix it. And seeing just the answer doesn't help us fix that. So we need pretty good explanation of the reasoning so that we can follow it. And I think business owners certainly would appreciate employees who can reason and give viable arguments on why a plan would work, or reasonably critiquing why they think a plan wouldn't work. Now, other standard practices, perseverance model, appropriate tools, precision, I think those are valuable skills to employers. Businesses certainly want people keeping their books to be precise. They'd like them to use appropriate tools. My wife's an accountant. She still wants to use an adding machine. A number of the younger accountants at the firm she's working at do everything on computers, but they've decided what's an appropriate tool for them. But they still use the appropriate tools and definitely have to be precise in their work. They have to persevere with the work. Most business problems don't come with an easy solution. There's no textbook, no place to check the answer. We've got to persevere, be precise to come up with an answer. The textbook is certainly an additional resource, so are the worksheets for you to work and continue practicing problems. And I have office hours in the tutor room available for that as well. If you, after class, are thinking, I don't think I got that, the tutor room can be very helpful, so can my office hours. The more you can come with, the better. If I can see a little bit of a start, then I can see, oh, here's maybe where you went wrong. Or here, did you think about doing this next? Coming with nothing isn't nearly as helpful as coming with an attempt, some sort of start on the problems. Now, there's a man called George Polya that came up with a problem-solving method that now bears his name, that to solve any sort of problem, I mean, he was thinking mathematical problems, but really any problem, you first have to understand the problem. So for this problem, let's think a little bit about going on a mission trip. So you're going on a mission trip, and you're thinking, I want to go and share the gospel. Well, there's sort of your problem. How are you going to share the gospel in that culture? Well, you need to understand that culture. So you kind of have to understand the problem. Then devise a plan. Most mission trips, you don't wait till you get there to come up with a plan. They go with a plan. You've done some preparation, devising the plan, but then when you get there, you carry out the plan. And see, and go out and meet people the way you had planned, share the gospel the way you had planned. But in fact, on most mission trips, you come back probably nightly and kind of look back. How did the sharing go? Were we able to connect? If not, what can we change tomorrow? In math, looking back is probably the step we do the least. Because a lot of math problems, especially textbook problems, I got an answer, I'm done. And we don't take the time to look back and see, how exactly did I do that again? Did I really understand everything I did? Am I sure I did all the steps correctly? We're just relieved, oh, we got an answer. But that looking back can really help us. So when I hand back homework, don't just say, oh, I got an 8 out of 10 and put it back and never look at it. Look closely. Why did I get an 8 out of 10? Obviously I missed something. We can learn from those mistakes. Where did I miss the problem? Why did I miss that problem? And if you're not sure, go to the tutor room, come to my office, so we can figure that out and look back. As I said, this can apply to any problem, not just mathematical, and I think those who have success with mathematical problem solving are recognized as good problem solvers in other fields as well. In fact, I would say most religions, in some sense, attempt to deal with the sin problem. I think all cultures understand that man has this problem. We have a sense of what we ought to do in various situations, and yet we realize there are lots of times we just don't do what we know we're supposed to do. We know we're supposed to do one thing, and for whatever reasons, we make a conscious choice. Sometimes it's not a conscious choice, but I think what really grieves God is when it is a conscious choice, we're going to do something else, even though I know that's what I'm supposed to do. My belief is Christianity gave God's plan, not one made up by man. God saying, yeah, I know you've got the sin problem. I'm going to send a Savior to meet the punishment of that sin. You need to accept that Savior. Together, then, we can work on that sin problem. Now, as we work at the textbook, as I said, I'd recommend buying it. And I did mention the 2 online versions, where you see it section by section, that has the exercises, and the version that doesn't have the exercises but has some worked out example videos. And the examples I picked to use in class are intentionally different from anything you see in the book. I don't want to redo things that are in the book. I want you to get additional examples. So the book can be additional examples. I am going to give answers on Blackboard and then solutions after the homework's returned. Now, another thing I've done, probably not as much as I've intended, and I'll try to work on that as the semester goes along, is some of you may be taking the GMAT exam at some point. I think it's the Graduate Management Assessment Test or something. No, Graduate Management Admissions Test. And they give a list of topics, and they have a number of math topics that show up on that. And some of these we will definitely be looking at through the course of the semester. We'll certainly be doing problem solving all the way. Certainly in concepts like working with functions, that's what we're going to look at today. In fact, this is about our first chapter, working with linear equations, quadratic equations, exponential. That's about our first chapter. Some word problems we'll see. So we're going to see a number of those as we review in business calculus. We'll see some word problems, things about profit, but even time, speed, rate problems. The basic formula for that is the distance equals rate times time. And that's a formula I think we're fairly familiar with. You know, if you drive 60 miles per hour for 3 hours, we can figure out how far we're going to go. We realize, oh, we go 180 miles. Or if you've got, say, 200 miles to go, and the traffic's kind of heavy, so you can only average 50 miles per hour, you might ask, well, how long is it going to take me to get there? And we can figure that out. How long is it going to take? 4 hours. Sometimes when I ask questions, there'll be A, B, C, D options to think about when we'll use the clickers, but this was not one. So 4 hours. So, or suppose we had 200 miles to go, and we need to be there in 3 hours, we can figure out, well, how fast do we need to go to get there? We can divide, and I think it's 66 and 2/3 miles per hour. So we probably go 70, just kind of be on the safe side, and hope the speed limit is 70 to allow that. But there's a very definite relationship between the distance, the rate, and the time, and as long as we know 2 of those, we can figure out the other. So let's sort of think of this a little bit more in light of what the GMAT calls a data sufficiency question. And the idea behind a data sufficiency question is you're given a problem. And you're not really so much solving that problem exactly. You're given 2 additional statements about that problem, and you're trying to decide, is the first statement sufficient? Does it give you all the information you need to finish solving the problem? But two's not. Or is statement 2 by itself enough to solve the problem, but statement 1 really isn't enough to help you solve the problem? Or both of them, do you need both of them to actually solve the problem? You can't do it with just one, you can't do it with just 2, you need both of them. Or could you do it with 1 and you don't need 2 at all? Could you do it with 2, you don't need 1 at all? So either statement by themselves would be sufficient, or perhaps neither statement helps you at all. So I think you can kind of see that there's actually a lot going on, a lot that we have to think through. But the idea of the data sufficiency question is not, can you solve this problem? It's, have we given you enough information to solve the problem? If 1 was all you had, is that enough information to solve the problem? If statement 2 is all you had, is that enough? So for example, and it uses this distance equals rate times time. So we want to solve the problem. How far are you going to go in 3 hours if we're going at a constant speed? Well, that certainly isn't enough information. So we add in statement 1. 1, we go 300 miles in 5 hours. We have statement 2 to consider. We can return in 3 more hours to where we started. And so our question then is, which of these A through E, and you probably, as you turn on your clicker, need to be sure to get back to the BB frequency, which of these A through E would be the appropriate response? Is statement 1 enough and statement 2 not enough to help us finish the problem? Is statement 2 enough, but 1's not enough to finish it? Do we need both of them? Is either one of them alone enough, or are both of them together not enough to solve the problem? Give you 20 more seconds here. Now, our reason for using the clickers, here was a problem. You had to think about it. But now we can see, well, how did everybody else respond? And I know more on how to talk about things. You know a little bit more on how to think about this, because you know, were you one of only 5 that answered C? Were you one of the 2 that answered E? Or were you in this majority? Now, the majority doesn't make it correct, but in this case, I do believe A is the correct answer. Because with statement 1, if we go 300 miles in 5 hours, we can figure out how fast we're going. 300 miles in 5 hours, we're going 60 miles per hour. And if we're going 60 miles per hour, we can figure out how far we're going to travel in 3 hours. Now, they don't ask us how far we travel, but we know they go 180 miles. So 1 is enough to finish this problem. So the question then is, well, what about 2? So if 2 is all we have, we go in 3 hours, we come back in 3 hours. Does that tell us how far we went? Does that give us enough information to figure out how far we went? And the answer is no. That doesn't help us. So 2 is not sufficient, but 1 was, and so A is the correct answer. We could finish and solve this problem. Notice this problem does not ask us to solve this problem. It's asking us which of statements 1 and 2 do we need to finish solving the problem. That's why it's called data sufficiency. Do we have all the information we need to solve the problem? We're not being asked to solve the problem. We did in this case. But do we have everything we need to solve the problem with just 1 by itself? With just 2 by itself? Either 1 by themselves enough, that'd be D. If only 1 does it, but 2 doesn't, then it's A. And that was the case here. 2 wasn't enough to tell us how far did we travel. Now, as we look at calculus, there are 3 major ideas we're going to be looking at and studying, and they are very much related. We won't always see the relationship, but the idea of where are we headed? Are we trending somewhere with our function? What is our rate of change? What is our speed? So in this formula, distance equals rate times time, we see the rate, or we could rearrange it and figure out the rate in terms of distance divided by time. But that's some information we may want to know. What is the rate? The other information would be, well, what's the accumulation occurs if we've got a non-constant rate of change? In a very real sense, the distance traveled here is our accumulation. You're going at a certain rate, you want to know how much distance piles up as we travel for a certain amount of time. And as long as the rate was constant, there's a pretty nice formula that tells us how the rate and the accumulation are connected. Just multiply the rate by time, and you get the distance. So in the case of a constant rate, the accumulation equals that constant rate times the time. And that shows how the 2 are related. The problem is going to be, well, not every situation is the rate of change constant. And also, especially if it's a continuous, we definitely need calculus. If it's discrete, we wouldn't necessarily need calculus. So let's think of a discrete situation. So suppose you were running a business, and you'd been, at the end of every day, figuring out, well, how much profit did we make today? How much profit did we make today? How much profit today? I'm calling that DP. So in terms of what I've got there, DP is the daily profit. And certainly that is something you'd be interested in a business. But something you'd also be very interested in the business is, well, after 10 days, how much profit have I made? So we'd be very much interested in the accumulated profit. That's what I'm calling P here. And if we think about it, I think we can come up with what the relationship between these 2 would be. If we had the accumulated profit, and we knew how much we earned after 10 days and how much we earned after 9 days, we could figure out how much we must have earned in the 10th day. What was the end balance sheet after 10 days minus what it was after 9 days? Well, that changes what you got that 10th day. Or, if you'd only been collecting, say, for 10 days, what's the profit on day 1, day 2, day 3, and that's when you decide to figure out what's the accumulated profit. You just add up those 10 days of profit. So what's that look like graphically? Here's the situation. We've got some discrete profits. So, say the first day we lost 6, just started the business. We didn't make money the first day. We lost some money. The next day we lost a little bit less. Well, that's good. At least we're headed in the right direction. So we lost about a little over 5, a little under 5. The accumulated profit, we've now lost a little over 10. And if we look at these may not look to match up exactly correct because actually these dots are from an underlying continuous model. I didn't start with the discrete model. I went from continuous to the discrete. But the idea here is we might be interested in how much are we earning each day. We might also be interested in how much are we accumulating. And certainly as long as we lose money, our accumulated profit is still going down. It only starts going up when we start getting some positive daily profit. Begin to pull ourselves out of the hole, and it doesn't happen immediately. Just because we start earning a little money, well, we still got a deficit to make up. But there's a definite relationship between the rate that the profit is changing, how much do we get each day, and how much do we accumulate. And that's really what we're going to be studying throughout calculus, not for discrete cases, but for continuous cases. And another question we're interested in, you're looking at the daily profit. It is trending upward. Does it keep going upward indefinitely? Does it level out at some? We'd also kind of like to know, maybe if it peaks and starts going back down, that'd be kind of bad. I mean, we understand, I think, what's going on at the beginning. We're just starting the business. We need to advertise more. We had some startup costs. We haven't generated traffic. But certainly at some point that daily profit better be positive or you're going to be in trouble. Only the government can continue to spend with a deficit. And in your economics classes you'll probably learn how long that could happen as well, to keep spending with a deficit. But lose money for a while, we definitely want to turn that, but certainly we'd be interested in, does this ever level out? We would also be very much interested in the question of, is this accumulated profit ever going to get up here and be positive? Would it ever level out? So there are a lot of questions we'd be interested in, but they are very much related to the idea of where are we headed, and how are things accumulating, and how are things changing? And those are the 3 key ideas of calculus. Because in calculus, we want to look at this picture not for discrete cases, but we've got something more continuous. So we've got a daily profit curve, we've got the accumulated profit, or maybe you're in a car, you're in reverse for a while, going backwards. You continue going backwards, but you're starting to slow down. You stop, and then you start going forward. And the question is, kind of how far is your accumulated distance? What distance have you traveled from where you started? If you're going backwards for a while, can you keep going backwards? You're going to get farther away from where you started, farther away, farther away, farther away. But you eventually do start returning to where you started from. So there's that idea of, how are these two related? And I'm going to try to come back to this idea repeatedly because it really is the basis of calculus. How are things changing? And how do we figure that out in a continuous case? And how are things accumulating? And how do we figure that out in the continuous case? And how are those two things related? How is the accumulation related to the change? How is the change related to the accumulation? It turns out that ultimately we will find relationships that go both ways. If we know the accumulated profit, we can figure out the change in the profit. If we know the change function, we can figure out the accumulation function. Now it's going to take us all semester to get those relationships. But that's what we're going to be looking for, is how is accumulation and change related? And when it's continuous, we can't just do what we did for discrete. I mean, with discrete, change we did with a subtraction. And accumulation we did with it adding up, with some addition. It'll be much more complicated when things are changing continuously rather than at discrete points. And that's what we're looking at with calculus. So, in calculus, the where we headed is called the limit. And we'll need to look some at the limit. The rate of change is called the derivative, and the accumulation is called the integral. So throughout the course of the semester, we'll encounter limits, we'll encounter derivatives, we'll encounter integrals. As we do that, we won't go into nearly as much theoretical justification as I would say in a Calc 1 course. But there are a few times we are going to look a little bit behind the scenes just to help us understand how are these related. Why exactly are we interested in the derivative? How exactly does that relate back to the discrete idea? I'll try to bring in some business applications, but there are times we won't see the business applications. But starting off at least, we're going to review some algebra first, just to kind of make sure we're all at the same point. Because, just as we did here with subtraction and addition, there are certain algebraic processes we need to understand. And on the GMAT syllabus, there are some things about being able to read information in graphic, numerical, verbal with that. And that ties into the first thing we're going to talk about, the idea of a function. When you hear the word function, what do you think about? If you had to describe just the English word function, how might you describe function to somebody else? Or where might we even hear the word function? Lab. What, a lab? Yeah. So, are you thinking like at the doctor's office and they ask you about how your bodily functions are working? Right. Okay. So in that case, your bodily functions, things your body does. That's kind of the idea of function. I mean, if you pull out your calculator, there are a bunch of buttons on there. They're all called function buttons. They all do something. You may not understand what they're doing, but they all do something. That's the idea of a function. It does something. Romans talks about just as our bodies have many parts, and each part has a special function. So it is with Christ's body. We're all parts of his body, and each one of us has a different work to do. So the idea here of function is we each have a function, we each have a work to do. And part of our calling is to figure out, well, what is our place in the body of Christ? What is God calling us to do with that? And how do we each do our part to make the body operate the way it's supposed to? But function is the idea of doing something. In architecture, one might talk of form versus function. Form is, the architect wants to make the building aesthetically pleasing. Function is the building better work and do something. I mean, if it just looks pretty, but nobody can use the building, then it's, becomes art. Which, there's a problem with art, but if you hired an architecture to build your office building, you didn't want art. You wanted a building that would be functional. Yeah, you'd like it to look nice as well, but it needs to be functional. And so we want that. And so we get the idea of function, that we do something. In mathematics, we need a slightly more specific definition of function. And that is, y is a function of a variable x if each value of x determines a unique value of y. And one interpretation of function that we'll use a little bit is sort of, we take x, we run it through some sort of machine, and it produces an output y. And the idea of this also is there's some rule going on. We may know the rule, we may not know the rule. But something's going on, we plug x in, it does something, and it gives us y. On the calculator, that's what happens. You've got a number displaying, hit any of the function keys, it'll show you a different number. You put anything into your function, the function does something and gives us some other number. So we would talk about x being the input, y being the output. But the two key ideas for mathematics is, for every input you plug in, you get an output, and you only get one output. Certainly in most places, it is very frustrating that if you do something one day and get a result, and do exactly the same thing the next day and get a different result, well, that's kind of frustrating. We typically, if we do the same input, we really want the same output. And for a mathematics function, that's what has to happen. Unfortunately, in our relationships with people, that is not what typically happens, because even if we do exactly the same thing, the other person probably is coming at it with a different attitude than they had the day before. So, we'll go back to a mission trip analogy. First day you see somebody, you talk to them, and they don't seem very receptive. The next day you talk to them, they seem a little bit more receptive. Well, from a mission standpoint, that's good. From a function standpoint, that is not obeying what happens with a function. Same input, we expect exactly the same output. To illustrate that, I want to talk about two functions that really are my favorite for illustrating the idea of function. One is what's called the gradebook function. And I'll apply this at the end of the semester. For everybody on the roll, they will run through the gradebook function, and that will pop a grade. So, Judy gets an A, John gets a D, Jane gets an A, etc. Now, I can repeat the outputs. In fact, I have to. There are 35 of you, if everybody's here. I only have 5 grades to assign. I've got to give some repeated grades. I don't have to use all the grades. I prefer not giving any Fs, but if that's the grade that comes up, that's the grade I'll assign. So I don't have to use all the outputs. But there are two things I cannot do in the gradebook function. I can't, if I've only got one person named Gene, try to give Gene an A and a C. For one input, there cannot be 2 outputs. And another way that we'll often look at functions is in a table, or ordered pairs like this: input and output. Each input is paired with one output. We cannot have an input going to multiple outputs. That is bad in the case of a function. With our system here at SVU, I can't even do this. If it were a paper system, I could attempt to write that Gene gets an A and a C, but the registrar would still call and say, what's their grade? Well, I want to give them both. I can't give them both grades. They earned 1 grade, and I've got to say what that 1 grade is. I can't say both. I also can't say Linda doesn't get a grade. The registrar would call and say, well, was she in your class? Yeah. What grade she get? I just don't want to give her a grade. Now, part of my job as teacher, part of the job of the gradebook function is each person has to be assigned a grade. Now, this part in mathematics we fudge with a little bit in that maybe we will take Linda out of the class. If she stopped attending, maybe she shouldn't be on the roll, we can take her out. And so there are times we can change the set of inputs, which is called the domain. The codomain is the set of possible outputs. The range is the outputs I actually get. So there are some places where we would change the domain and restrict it a little bit so that we can talk about a function. But every input has to go somewhere, and every input can only go to one other place as we pair it up. The other function I like to use is what I call the sheep-goat function, or what I think Jesus called the sheep-goat function in Matthew. Before him will be gathered all the nations, and he'll separate them from one another as a shepherd separates the sheep from the goats. And what I envision, everybody comes and sheep, goat. Everybody's going to be identified as a sheep or a goat. Nobody's going to come up and say, well, this is odd, you're on both lists. Single input cannot go to multiple outputs. It will either be sheep or goat. Cannot be both. Similarly, nobody's going to come and say, oh, don't see you on the list at all. Everybody's going to be identified as one or the other. So again, that pulls in the two key ideas of a function. Every input has to produce exactly one output. No duplicates of the inputs when we list them. No input missing an output. Now, usually for a function, we're given the input and we figure out the output. So typically we're going from the input, figuring out the output, which I would call evaluate. But there are times when we're told the output, and we want to figure out, well, what's the input, which would be called solve. Solving an equation. Here's the output we want. What was the input that gave that to us? My hope is you consider that with both the gradebook function and the sheep-goat function. On the gradebook, I think most of you come into a semester with some idea of what grade you'd like to achieve. And hopefully you'll look at the syllabus and say, oh, well, to get an A, this is what I'm going to have to do. I need to be in class because I don't want to throw away points on participation. I need to do my homework because I don't want to throw those points away. And I'll need to do well on the test, which if I've been doing the homework, I should be prepared to do well on the test. So we look at the output we want. What's it take to get that? Or if a B, etc. For that grade, what's it take to get it? Even more importantly for the sheep-goat function, I think the Bible clearly tells us what's required. To be a sheep, accept Christ as Savior, and do what and be obedient to His commands. To be a goat, reject Christ as Savior. Fail to accept Him with that. So it's very important on what are we going to do with Jesus Christ called to be Lord and Savior of your life, on determining that. But we can look at what outcome we would like. What do we need to do now for that to happen? And so, even more important than any other question we'll have would be that one, well, are you going to choose to be a sheep or a goat? And if you've not considered that question and made a conscious decision, I urge you to strongly consider that question. What result do you want? What do you need to be doing now for that to happen? Now, with mathematical functions, we've got some different ways we can describe the rules. We can do it with words or information. Part of calculus is also going to be figuring out, well, what information can we come up with from a function. We can put it in a table. Kind of already indicated that a little bit. We can do it in a graph. Certainly if these are numbers and these are numbers, graph's a very helpful way to do that. Or we can do it some kind of equation or formula. And these are just different forms, different ways of describing a rule. And sometimes one form is much more helpful than another form. So let's think about it with an example that I'm going to assume most of you are familiar with, the idea of the tithe. Verbally, how would you describe the tithe? I hope most of you were familiar. So what would you say about the tithe?
10% of your earnings.
10% of your income. So we have that verbal description, tithe is 10% of the income. We can translate that reasonably quickly into an equation. Tithe equals 10% or 0.1 times the income. We could build a table pretty easily then for a certain income. We could figure out the tithe. So if we earn $10, plug that in the formula, or think of the words. 10% of $10 would be $1. Now, if it was 20, we could figure it out. We could put together a table, and once we've got the table, The table, we wouldn't have to pick the income in order, although if we were going to build a very large table, we probably would. And we could graph that. And in graphing, typically it's the inputs on the horizontal axis, the outputs on the vertical axis. So when we put 10 into this function, we get out 1. That's what the table tells us. That's what the rule tells us. That's what the graph tells us. Put in 10, get out 1. Put in 20, you get out 2. Put in 40, we get out 4. 50, we get out 5. 100, we get out 10. But here's the case, definitely from discrete values, we definitely see there's a continuous model. In fact, our equation goes with a continuous model. So there are times, in a certain sense, we are most interested in discrete instances, but there's very much a continuous analog to that. Now, we were evaluating. You tell me the income, I can figure out the tithe. Income would be our independent variable. As we put that table, that's kind of what we're free to choose. And then we figure out the dependent variable depends on our choice of independent variable. What is our output? So what's the tithe? Some of you may have worked a retail job. I don't think this happens much now, but before the advent of computers, you get a subtotal for the transaction. You had to look at the table to figure out what's the sales tax. Even if you do income tax now, if your income's in a certain range, there are tax tables. If your income's in this range, well, this is how you figure out the tax. If it's in this range, this is how you figure out the tax. It gives a formula on how to figure out the tax. So there are lots of ways that we could use a formula or a table. Sometimes they're combined. But in tithe and many other cases, we could reverse this. And I think pastors could do this if somebody gave a tithe of, say, $60. We could solve this equation, tithe equals 10% of the income, by multiplying both sides by 10, and get that the income is 10 times the tithe. So if they tithe $60, the income must have been 600. And so we actually solved in our function rather than evaluate. Either one of those is a valid thing we could be asked to do. Now, there are some equations that end up not being functions. Things like x equals y squared. And if we're wondering, is y a function of x? Well, if we do a little bit of thinking, if x is 4, we don't know exactly what y is. So in terms of our picture here, x equals y squared, if we plug 4 in, well, we don't know if y is 2 or minus 2. That's a problem. In a table, if x is 4, y could be 2 or minus 2. That's a problem. Anytime we've got a repeated input, it can be a perfectly valid equation. There are a number of things we might be interested in doing. We can still draw a graph of this. It just isn't a function. So not every equation that relates x and y meets this mathematical definition to be called a function. On the graph, this fails what's called the vertical line test. If we can draw a vertical line that crosses more than once, it's not a function, because for that input, I don't know exactly what the output is. Maybe it's 2, maybe it's minus 2. And that maybe, that is not a function. You tell me the input, we need to know exactly what the output is. And if we're not sure, we don't have a function. We can certainly repeat the outputs, and that's okay, but we cannot repeat the inputs. Our notation, we will write y equals f of x. F is the name of our function. X is the generic name of our input. Typically, we will have f of x equals something. We'll have the rule written out for us. This is what we're going to do to our input x. But in some of our earlier notation, The input goes inside the parenthesis, f works on it, does something, and produces an output. So it's the independent variable that's going into our function, the dependent variable that's coming out. We could use other names for the function. We could use other names for the input. A lot of times we'll use time, t. We could use other names for the output. Could be profit, could be revenue, could be cost. Lots of other names for that. So let's look at a specific rule. F of x equals 2x plus 5. Our rule is named f. X is our generic input. This tells us what are we going to do to our input. In words, we could say, well, we'll double the input and we'll add 5. We could also say f evaluated at x. So we could then ask questions like, well, what's f of 1? So we plug 1 into the rule, we work it out. What do we get for f of 1? And again, your clickers probably have gone off. Be sure to get back to the BB frequency as you respond. Oh, I should also mention, if you make an answer and then decide, oh, I've answered incorrectly, as long as the clock is running, you can put in a different answer. It'll take the last answer submitted. And everyone correctly said it's 7. We just evaluate the expression. Well, the problem's not always that easy. So, and in fact, I try to make them a little harder. So what about f of negative 1? I also won't always let it run down to 0. So I want to be sure to get through a little bit more here, and we've got just a few minutes left. But 2 times negative 1 is negative 2 plus 5 does give us 3. So we have to evaluate it correctly with that. What would you say, though, about this one? What is f of d? Well, d is the input, we plug it in the rule. It's 2d plus 5. It is not a multiplication. So when we say f of x, it's not the f rule times x, it's the f rule evaluated at x. So whatever's inside here is what's replacing x in the rule. And maybe we can evaluate it more like we did with f of negative 1. Maybe we still have to leave it in terms of a variable. So what would you say about this one? F of x plus h. And it is 2 times x plus h plus 5. We replace the x with x plus h. The rule is twice the input plus 5. As the input is more complicated, the rule is still twice the input plus 5. We can simplify that down a little bit, but we won't always try to do that. Let's see. We are out of time. There is an assignment on Blackboard I'll double check that assignment to make sure you can do most of it. I may, look for an announcement on Blackboard because I may need to modify the assignment that's currently posted. Because I don't think we got quite as far through the material as I was hoping to. We should be able to finish it up on Tuesday and do what I plan to do on Tuesday. But I don't know that all the